Hello guys, I would like to congratulate everyone for completing the course Physics 22 successfully, and I would like to congratulate myself as well. So welcome back, and I hope you are all doing well. And so what I want to do in this video is basically I'm going to go over the final exam that we took in Physics 22, Term 1A2. So I'll be going over all of the questions, all the 30 questions, and that came in the final. And I will be following the form 00, like the one that is posted on the Physics 22 website. So the order of the questions will be the same as the form 00. So let's get going. Okay guys, so our first question over here is asking, so the question is saying that we have two waves, and these two waves are traveling in the same direction, and also we know that these two waves are identical, which means they have the same frequency, the same wavelength, and the same amplitude. Okay, so there is an equation for interference, like so the question is saying that if these two waves were to interfere, and the resultant wave is going to have an amplitude of Ym over 2. Ym is basically the common amplitude between the two waves. So Ym is the amplitude of the two waves, okay? So when these two waves interfere, we want the resultant wave to have an amplitude of Ym over 2. Where Ym is the amplitude of the two waves. Okay, so we know from our equation sheet that if we have two waves traveling in the same direction, and given that these two waves are identical, if they were to interfere, they were to interfere in such a way to result in a wave that can be described by this equation. So this over here is the amplitude of the resultant wave. Let's call it Ym prime. So here is the amplitude of the resultant wave, and here is the changing term, or the sinusoidal term. So we don't care about this term, okay? So we only care about the amplitude over here. So let's set up our equation. So we want this over here to be equal to Ym over 2. This here is given in the question. The question is saying that we want the resultant wave to have an amplitude of Ym over 2. So we let this amplitude of the resultant wave to be equal to the amplitude that we're given in the question, and then we just solve for the phase difference. So this is the value we're looking for. Okay, so the first step over here is to divide both sides by Ym. If you divide both sides by Ym, these are going to cancel out. And after that, you multiply both sides by 1/2. So multiply by 1/2 and multiply by 1/2. So this cancels. So this becomes this. And if you multiply 1/2 by 1/2, you get 1/4. And now you can easily solve for the phase difference. Take cosine inverse of both sides of the equation. And if you do that, you're going to have this equation over here. And then multiply both sides by 2. So you'll be getting that the phase difference is equal to 2 times cosine inverse of 1/4. And if you plug this into your calculator, you'll be getting 151 degrees. So the question, so this here is the phase difference, okay? This is the value that is asked in the question. But the question wants the answer in wavelength. It does not want the answer expressed in degrees. So what we're going to do is basically convert degrees into wavelength. So this here is an equation that you need to know. If you want to convert between degrees to wavelength, then you take the full circle, which is 360, and you take our phase difference over here. So the ratio between the phase difference and the full circle is equal to the ratio between the partial wavelength, or the, the displacement or the phase difference over one whole of the wavelength. So these two ratios must be equal because we know that. So if you go ahead and solve for x here, first you divide, these two are going to cancel out. And if you plug this equation into your calculator and you click shift solve, you'll be getting that x is equal to 0.42 of one whole of the wavelength. So the answer would be 0.42 lambda. And that is the answer we're looking for. Okay guys, so our second question over here is a pretty straightforward question. It's very easy. So the question is asking for the bulk modulus for a material where we know that sound is moving with a speed of this speed. So sound is moving through some material, and it's moving with this speed, okay? And the density of the material is given to us, and it's equal to this value over here. So we know that the speed of any sound wave can be given through this equation. So the speed of any sound wave is equal to the square root of the bulk modulus over the density of the material. The bulk modulus of the medium over the density of the medium. So the question is asking for the bulk modulus of the material that we're interested in. So we just solve for B, or bulk modulus. Square both sides to get rid of the square root. So we get the square over here, and then multiply both sides by the density. So we get here the density. So we get from this equation to this equation. And once we get to this equation, the question is pretty much solved. All you need to do is basically plug in the values. So the speed of sound is given in the problem, squared times the density. And if you plug that into your calculator, you'll be getting this value over here. And that would be your answer. Okay, guys, so for question number 3, it's also another straightforward question. So we're given two things. We're given a standing wave. So somehow a standing wave was formed. And we're given that the distance between two adjacent nodes in this standing wave is equal to 5.3 centimeters. So we know that the wavelength for this standing wave, it starts from here and ends here. Why? Because the wave starts like this, and then it repeats itself in this point. So the distance between two repetitions, when the wave behavior repeats itself like between 2 points, that is the wavelength. This distance is called the wavelength. So we know that the distance between two adjacent nodes in any standing wave would be equal to 1/2 of the wavelength. So in the question, we're basically given that lambda over 2 is equal to 5.3 centimeters. And we're also given that the speed of sound, or the speed of the wave in this medium is equal to this value. And we're asked to solve for the frequency. Okay, so first let's solve for the wavelength. And once we get the wavelength, we can easily solve for the frequency through this equation. So if we know that 1/2 of lambda, or 1/2 of the wavelength, is equal to 0.053 meters, then if you multiply both sides by 2, you'll be getting the value of lambda, or this value over here. Okay, so once we figure this out, we could easily figure the frequency because we have the wave speed and we have the wavelength. So for any wave, the frequency of any wave is related to the velocity of the wave and to the wavelength through this equation, okay? This equation is important to sort of memorize if you're doing waves. So if you just plug in your numbers, this one and this one into this equation, you'll be getting that the frequency is just equal to this value, and that would be your answer. Okay guys, so for question number 4, it says that we have some water, and the mass of that water is equal to 0.550 kilograms. And initially, the water was at 10 Celsius degrees. So what happened is that the temperature of the water was decreased from 10 Celsius degrees to 0. So change in temperature is equal to 10 Celsius. And after the water cooled down to 0 degrees, then it returned to, or changed to ice. Okay, so, and the question is asking how much energy we lost from the water, or how much energy we need to sort of do this whole process. So the first process that we have is basically when the water changed temperature from 10 Celsius degrees to 0 Celsius degrees. Then after that, we have another process, which is this change of status from being water, liquid water, to gas, which is solid. So the equation for change in temperature is this equation, and the equation for change in status would be this. When you change from liquid to gas or liquid to solid, or vice versa, you use this equation. So everything is given, basically. So change in temperature is 10. So we have this value, and we have the mass, and we know the specific heat of water is given in the equation sheet. And here for this equation, we have the mass, which is given in the question, and we have the latent heat of fusion. So we need to be careful because we have two types of latent heat. So we have latent heat of fusion, and we have latent heat of vaporization. Fusion is basically used for when water changes from liquid to solid, which means from liquid water to ice, and vice versa, from ice to water. So this is for fusion. Vaporization, we can use it when we have water, liquid water, and it becomes gas. And we can also use it the other way around, when we have gas and it changes to liquid water. So what we're interested in this question is latent heat of fusion, because we're changing from liquid to solid. So all you need to do is just plug your numbers to get the energy, the first energy, which is the energy associated with change in temperature, and the other energy, which is the energy associated with change from liquid to solid. So if you add these two energies up, you'll be getting this value, and that would be your answer. Okay guys, so question number 5 is a little bit more challenging than the other questions that we have solved so far. So the question says that we have 1 mole of gas that expands isothermally. So when we have an isothermal process, it means that the temperature is constant. So isothermal process means constant temperature. So the temperature of the gas stays constant, but the gas expands, which means it will have a final pressure that is different from the original pressure, and a final volume which is larger than the original volume. So we're given this in the problem, the work the gas does on its surroundings to sort of expand like that. And we're given the final pressure and the final volume of the gas after the expansion. So we're not given these values, these two values in SI units, so we have to sort of convert from atmospheric pressure to our Newton per meter squared unit. And we need to convert liters to meter cube. Yeah. So after we do the conversions, we could use this equation. So this here, this equation, gives you the work that the gas does on its surroundings if the process is isothermal. So if the temperature is constant, we could use this equation. And I took it straight out of the formula sheet. So you don't have to memorize it or anything like that. So, yeah. So we know that this part of the equation, nRT, is equal to pressure times volume. This is also straight out of your formula sheet. So we could rewrite this equation to be like this. We just replace nRT by pressure times volume. And once we get to this form, we know the work done, which is given in the problem. We know the pressure, we know the volume, pressure and volume. And we know the final pressure and final volume and final volume. So the only non-given in this equation is this here, which is the initial volume. And the question is asking us to solve for this value. So all we need to do is actually write this whole equation into the calculator and write here x in your calculator and then solve for x, and you'll be getting this value. So you'll be getting the value in SI units, which is meter cubed, and the choices in the exam are given in liters. So you just multiply that by 10 to the power of 3 to get this value in liters, and that's it. That would be your answer. Okay, guys, so question number 6 is a conceptual question, and it's about ideal engines. So we studied in our book that an example of an ideal engine, which is the Carnot engine. So the Carnot engine is the only example we have studied. So we have to know that an ideal engine is basically, or a Carnot engine is basically an ideal engine. And if you read the choices in the question, so the first choice, it says that an ideal engine uses only reversible processes. And that is true. Like this is explicitly written in your book that a Carnot engine or an ideal engine only uses reversible processes. So the second choice, it says it uses only irreversible processes, which is wrong. Like this is the antithesis of what we have written in the book. The third choice, it says it has an efficiency of 100%, which is not true, and it can never be true. Because we know that the efficiency of any engine in the world is basically the work we get over the energy we lose, or we take, actually. Yeah, so for any engine in the world, we have two parts. For any heat engine, so we have a hot part, a part with a very high temperature, and we have a cold part. So a part with a lower temperature than the hot part. And we have here some sort of medium. And this medium extracts energy from the hot part. We call it QH. QH is the energy extracted from the hot part. And once it's extracted, we get some sort of work here, useful work. But the sad thing is that some of this energy we extracted from here will be lost. Yeah, QL or Q lost. So this is the meaning of QH and QL. So the difference between QH and QL is the work done by the engine, which is here. Okay, so the efficiency of any engine is equal to the work over the energy that we get from the hot part. So, and for Carnot engines, we could expand this work to be written like this, because we know that the work is basically equal to QH minus QL. And if you divide both terms by QH, you'll be getting 1 minus QL over QH. So if we have an efficiency of 100%, it means that the efficiency should be equal to 1. And we know that it can never be the case because we have we have some value subtracted from 1. So choice number C is not correct. So the choice after it, it says that it has an efficiency of 50%. That is possible. Like we could have a Carnot engine with an efficiency of 50%, but not necessarily so. Like because for every Carnot engine, we have different efficiency. So it's not always 50%. So that choice is wrong. And the last choice is it says that a heat engine does not do any work, which is completely wrong because the purpose of any heat engine is to do work. So to say that a heat engine does not do work is nonsensical. And that's it. All right, guys, so question number 7 is a question that is testing you on Coulomb's law, or the electrostatic force between two charges, 2-point charges. Okay, so in order to solve this question, you need a little bit of imagination, like because this figure is not given in the question, but you have to sort of draw it yourself. So the question says that we have a charge Q1 placed a distance from the origin. So this is the origin. And we have another charge Q2 placed some distance away from Q1, and this charge Q2 is equal to -4 times Q1. And we have a third charge placed at the origin, and this third charge is equal to Q1, which is this charge. So we want to figure out this value over here, the distance between Q2 and Q1, in order to make the electrostatic forces to be equal to 0 on this charge over here. So we know that this charge here is negative, and this charge here is positive. So this over here is going to be pulling in this direction. And we know that this is positive and this is positive. So we're going, these two charges are going to repel each other. So we're going to have some other force over here. Let's call this force 1 and force 2. So we want these two forces to be equal. Otherwise, we're not going to have a net 0 force in the origin. Okay, so the force is equal to this here, this expression. So let's first begin by calculating this force, or F2. So F2 is this one. So the force between Q1 and Q3 is going to be equal to K Q1 squared over A squared. A squared is the distance between the two charges, and as it says in Coulomb's law, that the force is equal to K times the first charge times the second charge over the distance between them squared. Okay, so once we have set this up, we want this here to be equal to this. So this over here is F1, and it's the force between Q2 and Q3. So in order to sort of solve this, we need to use Coulomb's law, which is K times the first charge. The first charge is Q3, which is equal to Q1. So it's like having K times Q1, which is the first charge. So Q3 is equal to Q1, so and this is the first charge. The second charge is Q2, which is equal to -4 Q1. So times -4 times Q1 over the distance between these two charges squared. So the distance from here to here is A, and the distance from here to here is D. So the distance, the total distance between Q3 and Q2 is going to be equal to A plus D. Okay, so this here is the same thing as this here. And once you reach this sort of setup over here, everything in this setup is known except for D. So Q, the value of Q is not going to be used because it's going to be cancelled out. and k is going to cancel out too. So if you take the square root of both sides of the equation, you're going to get 1 over a is equal to 2 over a plus d. And you could solve for d in terms of a, or yeah, you could solve for d in terms of a. And if you do that, you'll be getting that d is equal to a. And therefore, the distance from the origin would be a plus d, which is the same thing as saying a plus a, which is equal to 2a. So we figured out that d is basically equal to a. So the distance between Q2 and Q3 would be just 2a. And that's it. That is your answer. All right, guys, so for question number 8, it says that we have some sort of charged particle. And this charged particle has a mass of 1.5 grams, and so it has some weight. So if you multiply the mass by the acceleration of the gravity, you'll be getting the force of the weight. And the question is asking us, what is the electric field that we should apply on this charge in order to counterbalance the weight of the charge? So we want a force, an electric force in the upward direction, and we want this to be equal to the weight or the force of the weight. So we know that the electric force is equal to charge times the electric field. So we let that equal to mg, which is the weight, and we solve for E, and we get this expression. And once we get this expression, we just plug in our values and we'll be getting this number. So this here is the magnitude. And how do I know the direction? So if you know that the charge here is equal to minus 3 times 10 to the 6, 10 to the minus 6. So we know that charge is minus or negative. If the charge is negative, that means the electrostat or the electric field force is going to be opposite to the electric field. So if we apply an electric field that is pointing downward, and we know that the charge is negative, so the electric force is going to be pointing upward. If the charge is positive, then the electric force would be in the same direction as the electric field. But in our case, it's negative, so the electric field must be pointing downward in order to counterbalance the gravitational force. All right, guys, so question number 9 is probably the easiest question in this exam. And it's asking us to solve for the electric flux. So it says that we have some cube, some imaginary cube. And we have, inside the cube, we have a charge, okay? So, and we're given the value of this charge. And we're asked to solve for the electric flux produced by this charge. So we know that any charged particle is going to sort of produce electric field lines inside the cube. And the flux is basically the lines that pierces the cube. Okay, so we have Gauss's law. So this here is Gauss's law, which says that epsilon naught, this is a constant, times the electric flux is equal to the charge enclosed. So if you divide both sides by this value, which is the constant, and then plug in the value of the charge, which is 2.5 times 10 to the negative 6. And if you divide the charge by the epsilon naught, you'll be getting this value. And that is the flux, the electric flux produced by the charge. Okay, guys, for question number 10, it says that we have some sort of sphere and we have some charge enclosed inside the sphere. And we know that the electric potential at the surface of the sphere is equal to V initial. So we want the electric potential to be equal to 2 times V initial, and we're going to get that by adding some more charge inside the sphere. And the question is asking us like how much charge should we add to the sphere in order to make the potential at the surface to be equal to 2 times the initial potential. Okay, so we have an equation straight out of your equation sheet. It says that the electric potential is equal to K times Q over R. So initially, we had K times Q initial over R. So R is the distance between the charge and the surface of the sphere. Okay, so this is here the initial sort of situation. But the final situation, we know that the final potential is equal to 2 times the initial potential. So this here is basically the final potential. And so this here is going to be equal to K times the final charge, final total charge that we have added, plus the charge that was originally inside the sphere, over R, which is the distance between the charge and the surface of the sphere. So in order to solve for this value, we're going to sort of divide these two equations, one by the other. So this is going to be cancelled, and this is going to be cancelled, and this is going to be cancelled. So we're left off with 1 over 2 is equal to Q initial over Q final. And if you solve for Q final, you're going to get this here. Q final is basically 2 times Q initial. What does this mean? Like, it means that after we added the charge and made the potential to be equal to 2 times the initial potential, we have the total charge to be equal to 2 times the initial charge, which means that we have added the same amount of charge that already existed in the sphere, or in other words, like we have doubled the charge. In order to solve this mathematically, like we could say that let's call this the added charge, and here is the initial charge. So the added charge plus the initial charge is going to be equal to the total or final charge, which is equal to 2 times the initial charge. Okay, so if you take this initial charge to the other side, you're going to have, in the other side, you're going to have Qi, and here you're going to get the added charge, and that is going to be equal to the original charge that existed in the sphere. And that is your answer. All right, guys, so for question number 11, we're given this graph of the electric field versus the displacement, or X. And we're given the electric potential at the origin. So the electric potential at the origin is 100, or minus 100. And we're asked to find the electric potential at this point. So in order to do that, we have to sort of use this equation that says the potential difference is equal to negative the integral of E dot dx. Okay, so the potential difference is basically V final minus V initial. In our case, V final is V3. So we're trying to figure that out. So V3 minus V naught. V naught here, it's minus 100 given the problem, is equal to negative the integral from 0 to 3 from this point to this point, which means the area of this triangle minus the area of this triangle plus the area of this triangle. Since the triangle is underneath the x-axis, we take the area as negative. Okay. Okay, let's now evaluate this integral, or this value. So if you want to get the area over here, you multiply, we use the formula for triangle area, 1/2 times the height, which is 100, actually minus 100, times when. So the area of this triangle is minus 100 over 2. And now, by the same exact logic, the area of this triangle, the big triangle, is 2 times 200 over 2. And if you sort of add these two values together, these are the areas of the two triangles, you'll be getting positive 150. And we have a minus sign from the equation. So the value of this sort of expression is negative 150. So now we can sort of replace this whole thing by negative 150, and we just did that, like it's here. And we already know that we took V naught to the other side, and we already know the value of V naught. It's given in the problem, and it's negative 50. So if you add these two together, you'll be getting negative 100, and negative 200, and that would be your answer. All right, guys, for question number 12, it says we have a group of capacitors, and all of these capacitors are identical. And it says that the equivalent capacitance, when you add these capacitors in parallel, is equal to 200 to 25, the equivalent capacitance when you add them in series. And we know that because these capacitors are identical, when you add identical capacitors in parallel, you just add them like this, and the result is going to be 3C, where 3 is N, and N is the number of capacitors. Okay, so this here is the formula that gives you the equivalent capacitance in terms or using the number of capacitors. And if you want to derive the same formula for series, we know that if you want to add two identical capacitors in series, you just add the reciprocals of the single capacitances, and so you're going to get 2 over C. And if you take the reciprocal of that to get the equivalent capacitance in series, you're going to get C over 2. And 2 here is N. It is the number of capacitors in the group. And it's like a pattern. Like if you add 3 capacitors, 3 identical capacitors, then you're going to have 3 over C. And if you take the reciprocal, it's going to be C over 3, and so on and so forth. So the formula is, for series, is C over N. So let's take this here, this. This is basically the capacitors in parallel. And this over here is the capacitors in series. And we know from the question that the capacitance in parallel is equal to 225 the capacitance in series. Okay, so now we have an equation, and we could cancel the C's. And then if you solve for N, you're going to be getting, you will get N is equal to 15. And that is the number of capacitors in the group. All right, guys, for question number 13, the question is asking about the number of electrons that flow in a wire. So the wire has a current of 10 amperes. And the question is asking how many electrons flow through the wire in 5 minutes. So we know that the current is defined as the charge over the time. And if you want to solve for the charge, we want to solve for the charge to get the number of electrons. So cross multiply, and you get the charge to be equal to the current times the time. And the current is just 10 amperes, and time is going to be 5 minutes times 60 seconds, because we want the time to be in seconds. And then you multiply everything out, and you'll be getting that the charge is basically 3,000 coulombs. Now, 3,000 coulombs, which is the charge, divided by the fundamental charge. The fundamental charge is basically the charge of one electron. So, if you divide the whole charge by the charge of a single electron, you'll be getting the number of electrons, which is 1.8 times 10 to the power of 22. And that is your answer. All right, guys, for question number 14, we're asked to find the value of this EMF, knowing that the current through this resistor is equal to 0. So what I'm going to do is I'm going to take some loops, this loop and this loop, and try to solve for that EMF. So let's now begin with this loop. Now going from here, from this point to this point, we're going from negative to positive. So we have positive 50, and then going through the resistor in the same direction as the current, so we have a negative sign over here. So IR, this is basically IR, or the current times the resistance, 100 times I1. And then we go over here, and we know that the current here is 0. So if you multiply I by R, you're going to get 0. So if you go through this loop and get back here again, you'll be getting 0 over here. Okay, guys, so according to the loop rule, it says that the algebraic sum of the changes in potential, if you go from a point and then return to the same point, the algebraic sum must be 0. And that's what we just did. We algebraically summed all the changes in potential, and therefore we have to get 0 on the other side of the equation. So through this equation, we could solve for I1, which is 0.5. Now, if you take the other loop, so we're going to take it from here. So if you move from negative to positive, you're going to have the EMF. And if you go this direction, you're going to have negative, the resistance times I2. So here, let's call it I2. And then if you go ahead and go through this resistor, so we know that the current is 0, so 0 times 200 is just 0. And then we return to the same point, and therefore the sum of these changes in potential must be 0. Okay, if you solve for the EMF, you'll be getting that the EMF is equal to 300 times I2. Okay, so how can we know what is the value of I2? Okay, so we know that these two currents are meeting in this junction, and therefore their sum must be equal to the current in this branch of the circuit. So I1 plus I2 must be equal to 0, because we know from the question that the current in this branch is just 0. So we know the value of I1. So I1 is just 0.5. So if you plug in 0.5 over here, you'll be getting that I2 is just negative 0.5. And if you plug 0.5 over here, you'll be getting negative 150. And that would be your answer.